Great. Well, thank you all for coming. It looks like we have a great group today, and I'm sure more will be coming in. Today, we're pleased to have with us Adarsh. He is a PhD candidate in computer science at Johns Hopkins University. He is currently advised by Suchi Saria and is a CERSI scholar affiliated with the Johns Hopkins Center of Excellence in Regulatory Science and Innovation. His research seeks to address challenges in developing safe and effective machine learning for healthcare using techniques from machine learning, causal inference, and robust optimization. His work has appeared in machine learning conferences as well as medical journals, including Biostatistics and the New England Journal of Medicine. Prior to his PhD, he received his BS from Vanderbilt University, and today he's going to be giving a presentation on addressing regulatory challenges for AI in healthcare, building a safe and effective machine learning life cycle. And we will have time at the end for discussion. However, he does encourage questions if they come up as he's giving his presentation. And both myself and Michelle will be monitoring the chat if people have questions as they come up. So with that, I'll turn it over to you.
Great. Thanks for the introduction. So I'm excited to talk to you about my work on building a safe and effective machine learning lifecycle for healthcare. It's an exciting time to be working on machine learning in healthcare because machine learning models are being actively developed and now deployed in a variety of healthcare applications, from detecting sepsis to COVID testing policies to identifying diabetic retinopathy. And so this promising potential has been shown primarily in what I call laboratory settings. So on simplified retrospective diagnostic tasks, it's been shown that machine learning models can achieve near human clinician level performance, again, on these somewhat simplified diagnostic tasks. And so spurred by this promise, there's been a growing number of FDA-approved machine learning-based medical devices, with over 350 such devices approved since 2016. So despite all this promise and potential, there's a number of concerns. So there's concerns about fairness and the inconsistent performance on different demographic subgroups, or the possibility of models propagating existing disparities that are in the data. Challenges to external validity, in which a model doesn't generalize beyond the particular site or data set that was used to train it. For example, an X-ray diagnostic system for predicting pneumonia from chest X-rays failing to generalize to new sites due to style-based associations that it's learned. Or policy shifts in which models implicitly learn clinical practice pattern-based associations, such as related to the timing and frequency of lab measurements. And as these policies shift over time or vary across sites, model performance deteriorates. So underlying all of these concerns is a fundamental question for the use of these models in healthcare. Will the model be safe and effective for its intended use? And safety and efficacy are at the core of regulatory policy in medicine. Historically, these are the principles that the FDA has used to regulate drugs and more traditional medical devices like X-ray machines. But in 2019, the FDA released a discussion document about a new regulatory framework for AI and machine learning-based medical devices, in part because of the sort of new challenges that are created by using these ever-changing technologies in a variety of different contexts. So with that as the backdrop, my research goals are to broadly build reliable machine learning models for clinical decision support, so models that perform to their specification, and to develop tools that enable us to establish their safety and efficacy. Doing this requires addressing technical challenges at all stages of the machine learning lifecycle, from learning algorithms that are robust to these types of changes and external validity, methods for stress testing and verifying their safety properties, and monitoring and maintenance strategies. So in this talk, what I'd like to do is I've worked extensively on safety and efficacy with respect to the problem of data set shift in healthcare contexts. And so what I'd like to do is overview some of this work. I'll first introduce the problem of data set shift and explain what it is. Then I'll talk about a class of failure preventative learning algorithms that I've developed for addressing dataset shift. Then I'll talk about evaluating model robustness to dataset shift, and I'll talk about briefly about some threads of future work. So what is dataset shift? Dataset shift is the problem of differing train and test distributions resulting from differences in the environment, so the population and settings that a model was trained in, and the population and settings that it encounters at deployment. These differences can arise as natural changes in the environment over time, or again, as these differences across sites as they manifest. And so the challenge of dataset shift is that a model that we learn from a particular training dataset can generalize poorly to new deployment environments when these dataset shifts occur. So how does dataset shift arise in healthcare specifically? In work with a really great team of clinicians, computer scientists, law and policy experts, we worked to create a checklist that starts to categorize the ways that dataset shift can arise. And so in this checklist, the taxonomy that we developed consists of primarily changes in technology, so shifts in the equipment used to collect the data, changes in population and setting, so shifts in the underlying patient population, the setting of use, the disease incidence, and finally, changes in behavior, so changes in the way patients behave, clinical practice, in financial incentives. These sorts of changes are the ways that dataset shift can arise in healthcare. So to see an example, in one study, researchers trained a model to diagnose pneumonia from chest x-rays. And they did this using data from a particular site. And what they found was that the model, in validation on held out data from the site, performed really well for predicting pneumonia. But what they found was that when they applied it to data from new medical centers that it wasn't trained on, the performance was significantly worse. And when they analyzed the model to understand these failures, what they found was that the model became over-reliant on these style features. So here, what's highlighted is this token that's telling you if this is a front-to-back or a back-to-front X-ray, so the orientation of the X-ray. And the choice of this token, the choice of a front-to-back or back-to-front X-ray varies for a variety of reasons. It varies based on the type of equipment that you're using, the type of scanner. It varies based off of the preferences of the technician, the policies of the department. And so what can happen is that an association between the orientation and these style features and pneumonia is actually very brittle. It's very likely to vary across departments and across sites. And so when a model learns to use this kind of style-based association, it harms its ability to generalize to new sites. As another example, this is from my own work, there can be changes in clinical practice patterns. So we had trained a model to use lab measurement information from electronic health record data to predict a hospital patient's risk of an adverse event. And what we found was that the model performed well on sort of the data close to when it was trained. But when we looked at its performance over time, there was a change point where its performance deteriorated significantly. And the reason is that the timing and frequency of these lab measurements can be very informative for prediction. So in this case, what's highlighted here is when lactate begins to be frequently measured, this actually corresponds with the region where the patient is deteriorating, as shown by their spiking creatinine. And so a model trained on this data can learn this association between the timing and frequency of these measurements. But these associations are also very brittle because they're based on these practice patterns that change as new guidelines come out, hospital policies change, and it causes an unstable association that leads to poor performance. So in the two examples that I just showed, what we saw was that the association between certain features and the label that we're trying to predict, say the target disease, has changed. And so these unstable associations result in what in machine learning we'd call an unstable learning target. So for the features X and the label Y that we're trying to predict, an unstable learning target is this distribution that we're fitting a model of that we're going to use to predict. And under a change in the association, what we have is that this distribution, what we want to use to make our predictions, will differ between the training data set and the target environment. And so a model of this unstable learning target, just fitting the data to the training data, will generalize poorly when those data set shifts occur. So how do we deal with data set shift? Most commonly, what's done is this paradigm called domain adaptation. And what I want to note here, and what's important to get, is that domain adaptation is this very reactive way of dealing with data set shifts. So we assume that we have access to our labeled source training data from essentially our home site, and that we have some amount of possibly unlabeled, so easier to collect data from the target environment. And so we actually get to observe some data from the target environment, and our goal is to optimize a model directly for that new site. So we get to, in some sense, react to the target data, observe the differences in the data distributions, and fix these errors once they've been observed. That being said, what a reactive approach entails is to tune or adapt the model for each given target domain. So when we think about the sort of modern models that are being commercially developed, say a X-ray diagnostic system is based in the cloud, and clinics all across the country can upload images from their clinics to this same cloud-based model. So requiring data from all possible target domains at the time of deployment is clearly not feasible. And so what we instead need to do is, like, we need to make sure that the models can work in some sense well out of the box, such that data from all target environments is not required. So as opposed to this reactive approach of domain adaptation that I mentioned, and what we need are these proactive approaches where we can specify desirable forms of robustness and think about preventing failure. So having a failure prevention paradigm in mind in order to improve the reliability of these systems. So now that we know what data set shift is, I want to talk about this class of proactive failure preventative learning algorithms that I've developed, and also walk through a couple of demonstration use cases. So the goal for shift-stable learning algorithms is, again, to implement this failure prevention paradigm where we want to learn models that are robust to likely problematic shifts. So this entails an approach in which we need to first anticipate and identify these likely problematic shifts and specify the ones that we want to protect against. So specify the behavior that we want from our model. Then we want to find a learning target. So again, we want to find this distribution that we're going to model and use for prediction that protects against those shifts that we specified. And then we want to actually fit and estimate this model. Finally, we want to be able to make some guarantees about the sort of the correctness of this model. How will it behave when these shifts that we've identified occur? Is it actually protected against them? So looking at this first step, anticipating and identifying likely shifts, the way that we're going to go about doing this is by thinking concretely about the differences that can exist in our data sets. So what we'll use are these causal graphical models of the data generating process in order to identify specific factors of the data distribution that we can then reason about. So what a causal graphical model does is, for these variables D, T, F, and X, it defines a factorization of the data distribution where each term corresponds to a variable given its parents. And so these factors, we can reason about these individual factors and whether or not they may shift and how we can protect against shifts in them. So thinking of a really simplified version of the pneumonia example where we're diagnosing pneumonia T from an X-ray X with style features F, where there's these differences in pneumonia prevalence and the choice of style features across departments D. So what we can see is that this graph represents sort of roughly the mechanistic relationships between the variables. So the X-ray image is a manifestation of a patient's pneumonia status and the style feature parameters that were chosen when taking the X-ray. And again, the prevalence of pneumonia and the choice of those style features varies on the type of department and the equipment that's used in the department. And so what we can do is we can reason about each of these factors and think about which of these relationships are going to be stable and are going to be things that we want our model to capture, and which of these are going to be unstable relationships that are likely to shift across environments. So while we expect that the way that pneumonia and the style features manifest on the X-ray image to be similar across hospitals, we know that the choice of those style features is highly variant by department. And so this is something that is going to likely be unstable. So now that we can reason about these shifts, we want to specify the shifts that we want to protect against. And so in doing so, what we'll get is this invariance specification. So we have this invariance spec, which is this graphical representation of the data generating process, in which we've identified those factors, those mechanisms that are vulnerable to shifts across environments. So in the X-ray example, again, because the style preferences can shift across departments, we want to be invariant to how these style features are chosen. But we still want to be able to capture information about how those features are related to pneumonia through the way it appears on the X-ray image. Again, for the orientation of the X-ray, that's important for understanding what we're seeing in the image. So the invariance specification is this graph and the set of 8 edges in the graph, these arrows which are marked unstable. And what it does is, again, thinking about those factors, is it defines a set of environments, so a set of hypothetical hospitals whose distributions differ in those unstable factors. So we're thinking about a set of hospitals who have what makes them different from each other are differences in how these style features are chosen. So the equipment that's used and the particular parameters that are used. Given that we have this specification, so we know what we want to protect against, now we want to, again, find this learning target. We want to figure out what is it that we can model that will be protected from those shifts. So the thing that we're looking for is a shift-stable distribution. So we want to find a distribution that we can model that is the same in all of those environments defined by that graph. So a distribution that is invariant to changes in the style feature policy. So to find this stable learning target, actually this graph is a very useful tool for determining whether or not a distribution is going to be stable. All you need to know is that you can look and see if a distribution can be represented on the graph through the paths that it uses for prediction. And all we need to do is check if there's any path used by this distribution which contains an unstable edge. So if we were to just predict pneumonia from the X-ray and the style features, there's this path from F to T through D that uses that unstable edge that we previously identified. And so that means that if I just fit a model using the X-ray or the X-ray and the style feature, the extracted style features, that distribution actually varies in each hospital where the style feature policies are different. But instead, if we actually have labels for the different departments, and if we also include the department as a feature when fitting this model, this by conditioning on this and including this feature, we actually block this path. And so this is a distribution that's stable. So T given F, D, and X is a distribution that's the same in all of these different environments that have different style policies. So now that we've defined what a shift-stable distribution is, and this is our goal, is to take an invariance specification and produce a learning target that we can fit that will satisfy that specification. So our goal is to retain as many stable edges as possible without using the unstable edges. Again, we want to capture as much of the stable information so that we can make more accurate predictions while still ensuring that we're not learning information that's likely to change. So to just show what this looks like, I've developed a number of algorithms that work like this. This is just to sort of demonstrate how we can do this. What we can see is if D is unobserved, so we don't see the department. What I showed previously on the was that predicting pneumonia from the style features in the X-ray, that distribution is unstable because of this path through the unobserved department. Instead, what we can do is, rather than the standard practice of just fitting a model to the data set, we can instead fit this interventional distribution, which corresponds to fitting a model at a hypothetical hospital in which we imagined that we had set the style features to be their observed values. So we imagine that we're fitting our class classifier between the style features and the department, because we're replacing that policy with this randomization scheme. So effectively, what we can do is we can separate out the effects of the style features on the X-ray from how the style features were chosen, and we can disentangle this information and learn a model that only uses these forward effects of how the style features affect the image, but ignores this relationship between the disease and the style features that's based on these changing policy factors. So once you have a stable learning target, then you need to fit it. And the main thing I want to get across is that we can be very flexible in how we do this. So everything that the sort of the distributions I was talking about up until this point are all very general. I didn't say anything about the form of these distributions or sort of restrict the kinds of models that we can use. And so you can think of the types of procedures that I'm talking about as these wrapper methods, where we have the appropriate model that we're using for our data, whether it's a linear model, a tree-based ensemble, neural networks. And what we're doing is we're changing how we're fitting those models. There's different ways to do it, but I'll just note that sort of an easy and what I use in the results I'm going to show is a simple data reweighting approach, where we reweight the rows of a data set and we fit a model using this reweighted data set. The last thing we wanted to talk about are the guarantees. So how do we, what can we say about this learning target that we found? And we can talk about its soundness, so its correctness, that the learning target that we've recovered is invariant to those specified shifts. So we've satisfied that invariance specification that we set out to create. That if we fail to find this distribution that we can model, so if the algorithm sort of returns that it failed, then we can actually say that there's no way to do this without more assumptions or more data. And we can also talk about the performance in terms of, we talked about this hypothetical set of different hospitals. We can think about, we can actually make statements about the worst case performance of a model fit using this sort of procedure across these possible environments, and show that it's better than just ignoring the shifts altogether. So the last piece to put this all together is, we've started with this graph, and it's how do we get this graph? And so there's no way to get around the importance of domain knowledge in these applications to be able to identify pieces of the data distribution that are of particular interest that may be unstable. But as we think about large, complex domains with like healthcare, and as we think about larger and larger feature sets, it becomes very difficult to sort of manually specify this from prior knowledge. And so fortunately, we actually don't have to just rely on domain knowledge. We can actually combine this with a data-driven approach called structure learning, where we look at the compatibility of the graph that we've learned, or sorry, we look at the compatibility of a graph with the independence information in the data. And so every graph implies a set of independences. And so we can actually test for the set of the equivalence class, the set of graphs, which share the implied independences, and then use these techniques across this equivalence class of graphs in order to find a distribution that will be stable to the shifts. So we can actually learn this graph from data, and that's what I'll show in a demonstration of this approach. So I want to talk about two pretty simple retrospective data experiments to show the potential of this The first is a semi-synthetic demonstration of the approach on a mortality prediction problem to just show the end-to-end workflow. And then I want to talk about an ongoing case study in which we're dealing with the, I talked about these, I showed this lactate example and talked about these missing, the informative missingness in electronic health record data. I want to show some preliminary results from an application to sepsis prediction. So for this mortality risk prediction application, we're thinking of a patient triage scenario in which we're predicting ICU patient mortality to identify the most at-risk patients. And the problematic shift is that, again, there are these clinical practice patterns where the timing and ordering frequency of lab tests can vary greatly. So what we want to know is, can we learn a model that's stable to practice pattern shifts and can generalize to new hospitals? To do this, we're considering the first 24 hours of data of a patient once they're admitted to the ICU, and we're predicting their ICU mortality. And we're using data from 3 hospitals in the Johns Hopkins hospital network, where our goal is going to be to look at the cross-hospital performance of a model trained at one of these hospitals. We used features corresponding to physiologic measurements, demographics, chronic diseases, the admission type, and then importantly, we synthetically exaggerate this lab timing feature, which is practice-based and varies by hospital, in order to create this shift and demonstrate the approach. So for learning the graph from data, I'll zoom in and sort of like show some pieces here. But we can take those features and again use this structure learning in order to learn a graph that's compatible with the conditional independences in the data. And we can combine this with some prior knowledge. So we're able to also provide a chronological ordering of some of the variables in terms of based off of the information that we have about a patient as they sort of go through the healthcare process. And so using this information, we can start to look at some of the insights that are recovered from the graph. So here in the top right, we have mortality. This is the outcome that we're predicting. And for example, there is this directed edge from age to mortality, which essentially indicates that age is a risk factor for mortality and that there's a direct association between these two. There's no way to make age and mortality independent. Similarly, there is a bidirected edge. So there's these 2 arrowheads between this lab timing feature and mortality. And what that bidirected edge indicates is that there's some sort of unobserved confounding relationship, that there's this spurious relationship between lab time and mortality, such that there's not a ancestral sort of risk factor type relationship between these two. And so what we can, so by looking at the graph, the final piece that we can actually get from it is candidate shifts. So when we have data from multiple sites, we can actually include the dataset ID as this indicator, this hospital indicator, and learn which variables are adjacent to that hospital indicator. And that indicates that we've detected a shift between, across the data sets in the distribution of those variables. So in this data set, the graph we learned showed that there were 12 candidate shifts, just some examples. Age indicating that there was a difference in the population, the demographics of the populations in each of the data sets. There were also some physiologic variables like bicarbonate and heart rate, which suggest differences in the severity of the severity of the diseases in the population, as well as this lab time feature, which we know we explicitly exaggerated in order to have it be very different across the hospitals. And so there's this variation across sites in that practice pattern-based feature. So next, we need to specify the shifts that we want to protect against. And a default sort of conservative choice is to say, okay, we identified 12 candidate shifts from the data, so let's just protect against all of them. And we'll see why that's not such a good choice. So instead, we can actually reason about those shifts and say that the physiologic shifts are clinically relevant. Again, they're informing us about the severity of the population, but these policy-related shifts are not. And so we want to only get stability to shifts in changes in the admission type or the lab timing distribution in the data. So what we did was we trained all the models at Hospital 1. This is the biggest hospital, and we evaluated its performance at each of the 3 hospitals. We considered 3 different models. The first is an unstable model. All of these models are tree ensemble models, so random forests, fit with the same hyperparameters. So the unstable model is we just sort of do classical supervised learning. This is essentially when people develop these types of models, they just we're fitting the data directly and ignoring the fact that we're going to be applying the model at these new hospitals. The second is we use the invariance specification based model in which we protect against only those 2 shifts that we identified on the previous slide. And then finally, we consider a conservative benchmark model, which protects against all 12 of those candidate shifts that were detected in the graph. So here we show the performance. This is the area under the ROC curve for the 3 different models at each of the 3 hospitals. So again, all models were trained at Hospital 1. So what we see is that at Hospital 1, the unstable model in blue performs the best, but it experiences significant deterioration in performance when we go from Hospital 1 to Hospital 3. By contrast, the conservative model that protected against all 12 shifts has low performance that doesn't degrade across hospitals, but is consistently very low. And so as this middle ground, when we protected just against those practice pattern-based features, we see that we get performance that also doesn't deteriorate across hospitals, but is actually competitive with the performance of the unstable model where we just sort of ignored the possibilities of the shifts. So what this shows is that stable models have performance which is more consistent across hospitals, but that protecting against too many shifts drastically reduces performance, again, because we're restricting the information that we're allowing the model to learn. And so this is why we want to include as much information as we think is relevant and stable when we're fitting these models. And we want to avoid discarding information that could be useful for prediction. So the second thing we measured was ranking stability. So the area under the ROC curve tells us about the overall discriminative ability of the models. But now we want to look at what the effect is on decision-making that could be made with these models. So what we did was we compared the correlations, the rank correlations of predictions for each of the 3 models. We trained the model at Hospital 1, we trained the model at Hospital 2. We predicted on the same set of held out patients. And we looked at the correlation in the ordering of the patients by risk for models trained at different hospitals. And so what this shows us is how much does the hospital that a model was trained at affect the ordering of patients by risk by that model. And so for the unstable model, it has very wide rank correlation, which is pretty low, while the 2 stable models, again, this model that protected against all shifts and the one that corresponded to the specification, has much more consistent rankings irrespective of where the model was trained. And so stable models will produce more stable patient orderings by risk, which can lead to more consistent downstream decisions. If I think about making decisions based off the top K% of patients ordered by risk, I will get similar results irrespective of where these models were trained. And so there's this balance between the stability of these predictions and the accuracy. As we saw, the conservative model is very stable, but has consistently poor discriminative ability. And so we're looking for this healthy median between the two. So this used this synthetic lab timing feature to just sort of demonstrate this overall approach. I wanted to briefly just show some results from the sepsis application that we're considering, where again, it's retrospective, distinguishing between sepsis and non-sepsis encounters in patients admitted from the emergency department, where the shift is in lactate missingness. So what we see is that when patients have lactate ordered, it's associated with it being a sepsis encounter, but this has changed over time. And so we want to learn a model that's robust to this type of lab test-based ordering pattern. We used, again, data from the Hopkins electronic health records for a model that's predicting up until time of sepsis onset or discharge using vital signs, lab measurements, and demographics. And we're looking at these two data sets where I pulled out some summary statistics to show that the populations are quite similar. The age and gender makeup is very similar. The sepsis prevalence is nearly identical between them. But what's different between them is that the rate of lactate lab orders is more than double at the second hospital. Or actually, this is over time. Sorry, in the later years. And so this is the second data set. And so we want to be able to account for these differences. So again, we consider a very similar setup to what I just showed for the mortality demonstration, where there's a baseline unstable model, which ignores the shifts. There's a robust model, which protects against the shift in lab ordering policies, which is represented by this distribution of the lab order given demographic information and sepsis status. And a benchmark model, which just completely drops the lab feature. So it only uses demographics and vital signs. Vital signs are not subject to much missingness. They're very regularly measured on these patients. And so we just ignore the lab features and thus don't have to deal with the potential for learning missingness-based patterns. So this is, the baseline unstable and the benchmark model represent two pretty simple approaches that we could use today for dealing with this problem. We could ignore the practice patterns and just learn them, or we could drop any features that could possibly be related to these practice patterns and try to make do with the remaining features. What I want to show is here for each of the models, baseline, robust, benchmark, we have the area under the precision recall curve, because this is a really skewed problem, a rare class problem. Here in blue, we have the models trained on dataset 1 and tested on dataset 1. Here we have in orange the models trained on dataset 2 but tested on dataset 1. And then on the right plot, we flip this. So now the orange models have been trained on dataset 2 and tested on dataset 2. And the blue ones have been trained on dataset 1 and tested on dataset 2. So what we see is that when a model is, when the baseline unstable model is trained and tested on a given dataset, it performs the best amongst all the models because it's just directly fitting the associations it learned in that dataset. But when we look at what happens when we transfer the models, the robust model has the best performance when it's transferred to the other datasets, where the other ones experience more, either more significant deterioration, or in the case of the benchmark model, which completely threw away the lab information, even when it's trained and tested on a single data set, it performs very poorly compared to the performance that we can get from the baseline or robust models. So again, we're seeing that the robust model has this sort of happy median kind of performance. Again, this is some preliminary results, so they're not very beautiful, but we get similar results for the consistency of patient orderings. and in going beyond these overall discriminative measures and looking at the alerting decisions, we're doing some analysis that for these classification metrics where we pick a threshold and look at the confusion matrix. And we see that what we're seeing is that there's less deterioration in the PPV, the precision of the model. We're testing this hypothesis that essentially we get fewer false positives on patients with lactate orders. So when I fit a model on the data set where we're learning this correlation between the presence of a lactate order and sepsis, what happens when we go to a shifted data set where lactate orders are much more common is that now this association is weaker. And so we're getting the issue that we run into is these false positives. So again, these are some preliminary results. The alerting analysis is really interesting because it can tell us something about the essentially the real performance that you would observe when making alerting decisions using a model, and not just how good are the probability estimates. So that was the overview of these proactive shift stable learning algorithms, which lets us specify shifts and find a learning target that protects from those shifts while retaining as much information as possible. I want to really quickly talk about evaluating model robustness to dataset shift. The challenges in evaluation are that when we evaluate models on datasets, we use cross-validation, the bootstrap, held out data, so that it looks similar to the training data. And this means that we're really assessing internal validity. When we're interested in external validity, how it will do it in use sites, really we're limited to the gold standard, which is to evaluate the performance on large, diverse, independently collected data sets, where we're limited by the availability of these data sets. It's costly to collect them. And it's hard to know what we're measuring if we don't understand how the data sets differ. If I just have a set of data sets, it could be that they're actually all quite similar. So even though a model performs well across them, it doesn't really provide as much information about the settings in which this model is safe to use. So with that in mind, we wanted to be able to answer, using the available evaluation data that we have, can we answer what differences across environments lead to model failures? How stable is a model's performance to changes in environment? And can we identify populations and settings in which the model performs poorly? To do this, what we want to do is a stability analysis in which we characterize how a model performs across a range of different populations and environments. To do this, we're going to identify subpopulations from the evaluation data set on which the model has its worst case average loss. So by specifying our loss function as subpopulation size, and a set of variables whose distribution may change, and a set of variables whose distribution should remain fixed, what we can do is actually define a general factorization of the data distribution such that the subpopulation corresponds to a worst case shift in this term W given Z. So if we specify W to contain demographic and comorbidity information, and we let Z be empty, then we're looking at a shift in the patient population defined with respect to subgroups based on demographic and comorbidity information. By contrast, if we look at a shift in a lab test order given patient history, we're looking at a shift in the lab test ordering policies. And so what we can do is, as like just to show how you can use this to perform a stability analysis. If we had a hypothetical model where we wanted to evaluate how its performance changes as we see shifts in the population mix, we would look at shifts in age and race, and we would see how for different population sizes, what is the performance, in this case, accuracy of the model. So for a subpopulation size of 1, that's the original evaluation data set, and so that corresponds to the overall performance. As we look at smaller and smaller subpopulations, we're looking at these worst case subpopulations corresponding to worst case distributions, which will produce poor performance. And for the sake of time, I'm going to go ahead and skip this, but we can use this to compare to sort of baseline standard of care models and identify regions of interest and look at the actual characterization and makeup of these worst case subpopulations. So we're applying this in ongoing work, but what I'd like to end on before I make sure there's time for questions is just to quickly mention some directions for future work. So we've looked at dataset shift and learning and evaluation. And when I think about the machine learning lifecycle more broadly, one key aspect is monitoring for dataset shift and test time failures. So to develop real-time methods for identifying individuals and groups of patient instances on which a model is uncertain and performs poorly. So knowing when to defer prediction because the model is uncertain about its prediction, as well as identifying when problematic dataset shifts that we didn't anticipate have occurred, and when there's the formation of new kinds of poorly performing subpopulations that we didn't identify during initial evaluation. Maintenance and model continuity, in which we develop strategies for improving and eliminating identified biases and poor performance in AI algorithms while maintaining their behavior continuity. So essentially, as we update a model, how can we make sure it's backwards compatible in the sense that it's not making mistakes that it wasn't making before, so that we're not introducing new problems when we're actually trying to fix these models. Longitudinal prediction and time-varying confounding, the applications that I showed, the applications that I discussed were these retrospective examples where we were looking at simple summaries of full patient encounters rather than the use case, which would be to make sort of like hourly predictions and track patients' risk over time. And so how can we extend these methods to consider the longitudinal patient risk prediction case so that we're resilient to these types of data set shifts where there can be complex relationships and how it affects the actions that appear in the data over time. And then finally, rethinking the role of machine learning in human interacting decision-making pipelines, where we figure out, model accuracy is just one piece of a decision-making pipeline when it comes to, let's say there's an alert and a clinician needs to make a decision about what to do based on this alert and how to actually treat the patient. And so identifying the properties that let us improve the outcomes of decisions so that we can augment clinician intelligence rather than just fitting the data, in which case what we're really doing is automating intelligence and potentially telling expert users what they already know. So with that, I'll end just to say that what I presented here today was a declarative approach in which we can specify desirable invariances that we want for dataset shift and proactively address it by proactively address these possible causes of failures. We can evaluate external validity using the variation within the data set and stress test robustness to these isolated distribution shifts. And then finally, I talked about how there's future opportunities throughout the machine learning lifecycle in order to improve the safety and efficacy of these systems in practice. So thank you, and I'm happy to take questions.
That was wonderful. Very impressive work. And I will just say, as an implementation scientist, I love your pragmatic approach to machine learning. It speaks to the clinician in me as well. So it looks like, does anyone have questions? Seeing lots of applause, though.
I have a quick question.
Mm-hmm.
Well, I have two disjointed questions, so you can pick and choose as you like. So I was wondering if you had any thoughts, thinking of this last section, about kind of alarm fatigue for the physicians and how you can balance that with accuracy, basically.
Yeah. Oops. Yeah, that's a great question. This last bullet about design incentives to maximize human-machine effectiveness and avoiding over/under-reliance. So this notion of trust and understanding sort of how users are using, say, the alerts of these models. So in the case of under-reliance, that can result from alarm fatigue, like you're mentioning, where if we're getting sort of too many useless or these false positive alerts, then very quickly, there's studies that show that basically people just start ignoring and completely not using the alerts. And so it's, I think we can distinguish between two things. We can have the accuracy of the alert in the sense of like the underlying prediction, if the alert is coming from a threshold on a prediction of the risk of a patient. We can have the accurate underlying risk prediction model, but we can have a separate alerting model. So rather than just a simple threshold, we can instead think about other factors involved to avoid under-reliance. So this is where one thing is like the uncertainty in the prediction. If understanding, maybe if the model isn't sure, that's a case where it shouldn't predict. Or it could be the case. I mean, I don't think there's like a single answer here. Developing these different alerting strategies is something that I think that will make the best use of these types of technologies, sort of dynamic alerting strategies that kind of adapt to the user in some sense, to figure out when it's effective. Because maybe the risk prediction is like very confident, but again, it's this problem of telling someone what they already know, in which case, okay, it buzzed, but like already the clinician was dealing with that patient, or like knew that that patient was was at potential risk. So all that is to say, I think there's a lot of interesting things to do there to consider the types of alerting strategies while separating that out from the notion of accuracy. There's no trade-off there, I don't think.
As I was listening to you, and you map out the features and the relationships between the features, I was wondering if you've thought about integrating some methods from system sciences, considering the complexity of the healthcare system, which in many ways you're trying to model in these relationships.
Yeah, can you I'm not familiar with the term systems sciences.
Yeah, well, I mean, in many ways, I guess, so system science really tries to look at all of the different processes and features of interest within a particular situation. Rather than distilling it down to a particular set, it looks at the dynamic interactions of all of those things and quantifies them. I'm not a system scientist, so I might be butchering it to a certain degree, but it looks like very much so what you're doing in many ways. So maybe it's more of a comment.
Yeah, no, I mean, I'd definitely be, I'm glad I'm learning something to look into, because I think there's different ways. I think there's absolutely different ways to think about, say, like the processes, so like the healthcare process, and how these, how it manifests and how it's like recorded in the data. So the graphical relationship I was talking about is like a very direct way of taking a very literal approach to thinking about the data being a direct observation of the healthcare process, and then just directly relating it. But if there's these other approaches, I think that what I would imagine will be good is that they'll sort of trade off the types of assumptions that they're making when you're kind of simplifying to take a complex system like healthcare and model it. There will be different trade-offs that we have to make when we make any sort of modeling choices. And so I think, yeah, I definitely will look into that. I'm just not familiar with the types of things studied there.
I have another question if nobody else wants to jump in. So I'm really interested in also these like invariant representations. And I was wondering if you ever think about using more generative models. So me personally, I'm interested in kind of domain adaptation across sequencing technologies. So say you have two different sequencers and you only have one biological condition observed. So you would want to kind of like impute or like generate the missing technology and the missing condition. So do you ever think about these techniques or have any ideas about those sort of ways that you can use domain adaptation in that case?
Yeah, that's a really good question. It definitely differs depending on the type of scenario, in the sense of what I was talking about. If we have access to some amount of like this target data versus not. So like if we have the ability to borrow from, say, other environments, or in your case, borrow from these other sequences to learn from, then I think sort of more classical transfer learning or domain adaptation can be used to try to essentially automatically find some like similar patterns across them. Where the challenges with the representation approaches, and the one thing that I'm a little wary of, but I'm interested in sort of bridging the gap, is in understanding the the assumptions that are baked in when we say that the representation is invariant. What does it actually mean with respect to our data and our problem? Obviously, if we have if we're not thinking about this high dimensional data, this is a problem with images. So I sympathize when thinking about imaging data. But if I learn a representation from this kind of data and it's invariant, great, I have an invariant representation. But what is it invariant to? Like, what are the invariances that I've learned? And so if we don't have a clear indicator of, like, say, the outside interventions that make the different things that we're learning an invariant representation of different, then I think it's hard to in some sense, depending on what you're doing, make useful or sort of confident statements about then like the downstream conclusions that you're making. So that's the one sort of caveat I would make to like those kinds of approaches, and just being a little bit careful about connecting it back to like, what is it invariant to when we talk about invariance.
Well, we are at the top of the hour. I sense a lot of enthusiasm in the room, well, virtually, for your work, and I share that. Thank you so very much for coming and teaching us something that we didn't know about.
Thanks for having me.